Okay, in the last video, we saw that the Maxwell equations led to the production of electromagnetic waves, and we saw that those electromagnetic waves propagated at the speed of light. At the time, I made the observation that this was made without reference to an observer. In a bit of a roundabout path, we're going to follow up on the consequences of that and see how that leads to Einstein's theory of special relativity. But to help set the stage, first thing I want to do is have us realize that there is some incompleteness to the Newtonian mechanics we've been learning so far. So this end, I want you to think about a problem where we have an electron gun. So remember, an electron gun is a device where we have a little filament that we heat up. Electrons boil off of it. So some random electrons will come off. And then we go ahead and accelerate it through a known potential difference made by a couple of plates. Oops. There we go. And on the business end of the electron gun, there's a little hole drilled through the plates. So what will happen is most of the electrons will get accelerated from the negative plate to the positive plate. And most of them will just land on the positive plate, but every so often, one of them will shoot through the hole and get moving, and that electron will go flying off at some speed v that we want to find out. So you'll remember we've done a problem similar to this before, and so for this particular problem, I'll be wanting you to pause the video and solve for what would be the final speed of our electron if it's going through a 1.022 million volt potential difference. And remember, when we introduced the electron volt, we found at the time that we could express mass in these really funny units of EVs per c squared. And it'll be helpful to remember that the mass of the electron is 511,000 EV per c squared, where c is the speed of light. So I would want you to find v as some number times c. So go ahead and pause the video, work this out, and we'll get back together. Okay, so when you did this, I'm hoping that you got that it was going at 2 times the speed of light, which is not physically possible, but we'll get into that. But first, let's just review how to solve the problem. So what we can do is we can equate the initial potential energy of the electron, which is E delta V. We can equate that to its final kinetic energy, 1/2 mv squared. So we can solve for the speed and get that as 2E delta V over m, and then we take the square root. Okay. So remember, the joy of working with the EV units is we don't have to substitute in any value for E. The E in EV is literally there just to cancel. So this will be 1,022,000 volts. We're dividing by a mass of 511,000 EV per c squared. Oops, there we go. So This E and that E cancel. The volts cancel. 1,022,000 divided by 511,000 is 2. 1 over 1 over c squared is just c squared. So we're left with this being the square root of 4c squared, which is 2c. All right, there's a problem with that. The problem is this doesn't actually happen. If we accelerate an electron through a 1.022 million volt potential difference, and that is something that is very straightforward to do in a lab setup, and we measure the speed, what we get experimentally, is that it is approximately 0.943 times the speed of light. Okay, so what does this mean? Well, one of the things it means is that Newtonian mechanics is incomplete. Now, it is a very successful model, but we have found an experimental contradiction to it. Newtonian mechanics predicts that this electron would be moving at 2 times the speed of light. We actually do it. It's 94.3% the speed of light. And remember, first and foremost, physics is an experimental science. If even one experiment contradicts things, then that model is wrong. So we know that Newtonian mechanics is wrong, but it can't be that bad. It works incredibly well as long as things are going slow. It seems like where the breakdown is where things are going fast. So what we need is a new model. And it has to satisfy what's called the correspondence principle. This says that whenever you have a new model, you have to show that the old model works in the limit of where the old model that the old model is a limiting case of the new model in the regime where the old model worked. Probably the best example I can think of this is the transition from the geocentric to the heliocentric model of the solar system. So in the geocentric model, you would have the Earth in the middle, and then somewhere out over here was the sun orbiting around it, like so. In the heliocentric model, we have the sun in the middle, and the Earth orbits around the sun other way around. Okay. So the thing is that the distance from our sun to the nearest star is very large. And so with the exception of a couple of nearby stars moving very quickly, we can pretty much say, at the scale of, say, here's a nearby star, and here's us. I'm trying with me even just drawing one dot here for the Earth and the other dot here for the sun, I'm drawing them too far apart. And so if I'm looking at even a nearby star, let alone the stars far away, um, there's really no difference in how the motion of the distant stars work, and both models agree very well. In fact, if you happen to visit a planetarium that's still for some reason hasn't upgraded its old electromechanical projector to a computerized projector, those old electromechanical projectors are actually built around the geocentric model of the solar system. And it's used because it's easier and it gives a plenty accurate enough answer. Now, where things break down was had to do with what was called retrograde motion, and I will happily let an astronomy professor get into that. But long story short, when you look at the position of a planet night over night, usually between successive nights, the position of the planet is progressively more eastward. Um, now, over the course of a night, it'll rise on our eastern horizon, sun on our western, but its position against the distant stars usually moves more eastward every night, except when it undergoes retrograde motion. When it undergoes retrograde motion, that's where for a couple of weeks or so, the planet suddenly seems to be going westward against the distant stars instead of eastward. Now, in fact, that's actually where the name planet comes from. It comes from the Greek word for wanderer, and it's referring to the fact that these planets would wander in the sky. That was the retrograde motion. So I won't get into the history of it, but there were attempts to model um, retrograde motion using the geocentric model, but it led to just a giant mess. It became very incoherent, and it became very clear to astronomers that that couldn't possibly be the correct answer. The heliocentric model, on the other hand, provides a very um, good answer for it. Um, in the heliocentric model, it says that this apparent backward motion happens when you're passing the planet. So, for instance, if you're driving down the freeway and you're passing a car, now I would not recommend doing this while you're actually driving, but say if someone else is driving, if you're passing another car, if you focus off against the distant background, the car you're passing will appear to go backwards. And that turns out to be what retrograde motion is, and it's very cleanly explained in the heliocentric model. So the heliocentric model fixed the retrograde motion problem, but it satisfied the correspondence principle in that when we looked at the motion in the sky of distant stars, you got basically the same answer because the Earth and the Sun were so close to each other that it was effectively no significant shift of viewpoint when looking at a distant star. So that's an example of how the retrograde motion, of how the correspondence principle works. In the case of relativity, which is what we're going to use to replace Newtonian mechanics, we're going to require that special relativity converge into Newtonian mechanics when things are going very slow compared to the speed of light. Okay, so over this video series and the next one, that's what we're going to build up, and then we'll see what the consequences of that are. Now, before we delve deeper into into this, I think this is a good point for me to talk about defining the inertial observer and the term event. So we'll start with defining the term event. When used in relativity, what that means is something that we can localize in space and time. So we should be able to write it as an x, y, z, t set of coordinates. Um, so it has to have a specific location, space, and a specific time it happened. The usual mental picture all you have is of a firecracker going off. Cracker. Some firecracker goes off somewhere. Lots of festive colors. This firecracker exploded at a very specific time, and it also exploded at a very specific position. Combine the position together with the time, that's what we call an event. Okay. The tougher one is defining an inertial observer. It turns out that when we think about what we see versus what we observe, these aren't quite the same thing. Not as how a physicist would use the term. I'm aware that in fields such as biology, these are absolute synonyms, but not to a physicist. See means what you see with your eyes. And by eyes here, I'm extending this to allow for whatever sort of hyper sophisticated recording equipment we might need to see things happening at a very fast rate. But that's what we mean by that. Observe is what happened after correction for speed of light delays. So the best example I can think of is not so much from dealing with the speed of light, but the speed of sound. There's an absolutely beautiful phrase that Mark Twain used in one of his novels describing how wide the Mississippi River was. And in his description, he said it was so wide that a person sitting on that if you're on one side of the river going down the river and you looked across the river and you saw a person splitting wood, their arms, they would person splitting would have their axe go back up above their head before you heard the wood split. Now, asking rhetorically, did the wood splitting and the generation of the sound, were those totally different things? No, of course not. We know that the wood splitting and the sound being generated happened a ways apart. So here we have our log. Here's our hero stick figure guy with stick figure axe. And they're splitting the wood. So you're over here on the other side of the Mississippi River. There we go. So when we start splitting the wood, sound waves get produced, but they take time. These sound waves travel at around 343 meters per second or so, but they're traveling at that speed. So the Mississippi River is very wide, and it can actually take a few seconds for the sound to make it to your ears. And so that would be what you see. You see the wood get split, and eventually also note that a few seconds later, there was sound. What you observe, though, is that the wood was split at the that the sound was made the same time the wood was split, because you then pull out your notepad, you calculate how long it would take sound to cross the Mississippi River, and you work out, oh, the delay between me seeing the wood get split and me hearing the wood crack is exactly what I would expect for the sound to make it across the Mississippi River. So I conclude that the sound being made happened at the same time as the wood being split. You would observe that the sound and the split were simultaneous. So you see one and then the other, although you're seeing it with your ears, I guess. But you observe that they happened at the same time. And this is the usual picture that most books do. Now, when I learned this, I learned another picture that I personally find very helpful. So I'm going to present it as an alternate in case you find it helpful too. In this picture, what I imagine my observer to be is a lattice work of clocks. So I'm just drawing a bunch of clocks, and I'm trying to get them all to read the same time. Oops. Something like that. And neatly organized on a lattice. And I imagine little leprechauns sitting in front of each of these clocks. Now, initially, you have to figure out how you're going to get all the clocks to tick over at the same time. But that's pretty straightforward. What will happen is the leprechaun at the central master control clock located at 0, 0, has the responsibility of lighting off a firecracker when their clock is at t equals 0. Now, what will happen is when they light off that firecracker, light will propagate out in all directions around. Now, the leprechauns sitting at all the other clocks, they've already pre-computed how long it will take light to travel from the master control clock to the clock that they're sitting in front of. So let's say over here, this leprechaun works out that's going to take a second for light to travel from the master control clock to, well, actually, let's say like a millionth of a second. This leprechaun works out that's going to take a millionth of a second for light to travel from the master control clock to their position. So what they do is they preset the clock to a millionth of a second. Then when they see the firecracker go off, they just plain start their clock. And since their clock is preset to a millionth of a second, that's also what the clock here would have been reading, because light would have made it from here to here a millionth of a second after the firecracker went off at t equals 0. So this clock will have advanced by a millionth of a second as well. And maybe this leprechaun out here works out that they're going to have to set their clock to 1.4 times 10 to the negative 6 seconds because of the extra distance. But that's fine. When the light wave makes it to them, they start their clock, and that again here, this clock would have advanced to t equals 1.4 times 10 to the negative 6 seconds at the same time the light pulse makes it here, where the clock was preset to that number. So you wait a good long time for the light wave to propagate through the whole lattice work of clocks, and then what you have is a whole collection of clocks that are all ticking over at once. So that's sort of the calibration phase of this. But then what that means is for doing the observing, you don't have to take into account speed of light delays anymore. Um, because the idea is that this lattice work is so finely packed that there's always a leprechaun sitting in front of a clock wherever you happen to need one. So if, let's say, a firecracker goes off right over here, the leprechaun right here can report, hi, I'm the leprechaun at x equals plus 1 meter, y equals negative 1 meter, at t equals 7 times 10 to the negative 6 seconds, a firecracker went off. And since the firecracker went off right where the clock was, there's no speed of light delay. And so you can think of the observer as just this entire collection of clocks and leprechauns. And just wherever the firecracker goes off, the event occurred at the coordinates of that leprechaun's clock at the time read on that particular leprechaun's time on that particular leprechaun's clock. I don't know. It's one of these things that it seems to be about a 75-25 split, which way people like it. If you like sitting back and just thinking about the time it takes for uh, light to travel to a particular observer, you can certainly do that. Or if you prefer to think about the last work of Lox with their attendant leprechauns, that works too. I don't care which way you do it. Okay. So in the next video, I'm going to go ahead and review the Galilean velocity transformation from mechanics. And then we will see how the Maxwell equations combined with the Michelson-Morley experiment will require us to have a rethink of that and the consequences of that. So catch you in the next one.